Okay, good morning, good afternoon, or good evening, depending on where you are. We're up for the next session, and this talk is from Clément about its traverse. Clément will introduce himself in the recording, so I will leave that up for him. On the YouTube channel, you can chat if you have questions or remarks. Clément is watching as well, so he will answer. Or you can use Twitter and use the 5Ds hashtag to get involved in our conversations. For now, I wish you all fun with Clément and good luck, break a leg.
Hi everyone, I'm Clément. Today I will talk to you about a wonderful function called traverse. So quickly, I'm Clément. I'm mostly active on Twitter, so if you want to chat about DDD and functional programming on Twitter, hit me up. I will be delighted to chat with you. I'm trying to blog both on my blog and on my company's blog. Roughly, I'm mostly a functional programming guy. I used to be CTO like a few years ago, and I'm currently working mostly with Haskell, but I've worked with a host of different languages in the past: Scala, JavaScript, a bit of Rust, stuff like that. I'm working for a company called FretLink. We operate in the road freight domain. We match carriers and shippers and try to enable small carriers like family-owned company to work with big shippers like retail companies, for instance. Our product used to was created with a Node and Mongo platform, but more recently we are creating new services backed by Haskell and PostgreSQL and a bit of Rust on the side. First, disclaimer: I'm not the regular DDD guy. I come from FP, so I may have heterodox opinions on some things, but I think that's a nice thing to compare opinions and views. I want to reassure you first, DDD and FP are not opposed. Even though most of the DDD literature is based on object-oriented languages, I think FP, functional programming, maps really well to domain-driven design, and in some cases, and many cases, better than object-oriented, I find. The relationship between functional programming and domain-driven design has been explored in two really nice books. One called DDD Made Functional, which is geared toward using a functional language in a DDD setting. So it's really a strong DDD mindset. And the other one is more about doing DDD coming from FP mindset. So the first one is in F# and the second one is in Scala. Both books are really great. Myself currently, I'm a bit more aligned with the second because I have a strong functional programming backend. So let's start with something close to DDD in functional programming. It's called algebraic design. The idea is to model the domain as an algebra. An algebra, roughly speaking, and I hope there is no mathematician in the audience, roughly speaking, we can view it as a collection of function types. So you describe all the operations in your model as function types, and the whole thing is your algebra. And once you have your algebra, so functions and laws, so the properties of each function, then you can go on with implementation. But the design itself, it starts from the types, and it's something that happens quite naturally in typed functional programming. So naturally, actually, that many people don't use the term algebraic design. They just design code because that's a natural way to do it. And that's why I liked DDD, because it was quite aligned with that, and it did put some words on concepts that were just occurring naturally when working in FP languages. And algebraic design has quite a big difference with normal DDD, as it is commonly practiced. Is that it relies on common abstractions. Thanks to the nice properties of functional programming, in functional programming we are able to extract powerful and robust abstractions. So abstractions so good that they are common across projects, and it's not like design patterns where you re-implement them. They are so well defined you can just use code to do that, and they are so good that they exist across programming languages as well. So there are abstractions that are essentially the same in Haskell, in Idris, or in PureScript, or in Scala, and that's a sign that the abstraction is not coming from the language. It's an abstraction that's already there and useful, and we map it to a language. So it's still close to DDD because we model an existing thing inside the language. We don't extract stuff from a language. And in functional programming, we tend to have a ubiquitous language that includes these common abstractions. So they become part of a shared vocabulary, and it's often the case with algebraic design. These abstractions are part of the model itself. So that may sound scary for DDD practitioners, because normally the ubiquitous language and the model should not include technical programming terms. It should be defined only in terms of the model and the domain itself. But here it's a trade-off, because these abstractions are really powerful and really pervasive. So they also happen in the domain itself. So it's kind of useful to be able to rely on them because they tend to emerge even in really different domains. Sorry. So for instance, let's say I have a money type. I can say it has a monoid instance, and in an FP setting that would be enough. Or I can say that I can add 2 amounts of money to get a new one, that I can talk about a null amount of money, and that if I add money, 3 amounts of money, I can group the additions in 2 ways, called associativity. And of course, if I add 0 money to any amount of money, I get the original amount of money. So both are equivalent. One fits in a single word that is commonly understood. The other one is a bit more unrolled. It's a bit more readable because you don't have to know what a monoid is, but they are essentially the same. Once again, it's all about trade-offs. If you maintain a set of common abstractions that are well known within your team, then you gain time and you avoid being unclear, because you are extremely precise. These names and these abstractions are really well defined, they're really rigorous. But of course the trade-off is that it's an upfront cost, and you have to make sure everyone in the team knows it. And even more, if you want to put that in your model, you have to make sure that your domain experts knows some of these abstractions, and that can be hard and costly to do. Okay, I promise I'm getting to the point. I felt it was interesting to to be clear about how I see FP and DDD, so that you can better understand why I'm talking about all this. Today I want to talk about two abstractions coming from functional programming, and maybe you can use them in your Ubiquitous language, or maybe just knowing that they exist, it can help you a lot with implementation, and that would be great already. Even though you don't use them to communicate, when working on code, having these functions and these helpers around, it's really great, because it allows you to offload lots of conscious work to your unconscious and to intuition. So you can skip all the uninteresting details and say, oh yes, this is just traverse, and you put a traverse, and then your implementation is done. You don't have to think about all the details. So why traverse? Why is this function? It's really pervasive. It's a function that will come up in many different cases, and I like it because it's great to showcase how much you gain by using proper abstractions and functional programming. Functional programming is great at turning really abstract concepts into really concrete benefits, and Traverse is great to show that. But more importantly, I wanted to talk about Traverse because it's a joke. Every time someone says, I'm doing this operation, it feels something like more general that the code I gave, but I don't see what. And most of the time you can answer, yeah, it's Traverse, and it would be actually Traverse. It's really pervasive, but it's pervasive, it is not immediately obvious, and that's why the joke is funny. I could say, yeah, I don't know how to do that, but yeah, try a for loop. And yes, in imperative programming, most of the time a for loop is what you do, but it's not funny. Everybody knows that for loops are quite essential to programming, so why bother? Okay. I know this has been a really long introduction, and I'm a prog rock fan, so I know a thing or two about long intros. Let's get to it. Here is a function called Promise.all. It comes from JavaScript, and what it does is allowing you to collect multiple promises into a single one. So the arguments it takes here is an array of 3 promises, and it returns you a single promise with all the values. So it awaits for all 3 promises, and when it has its 3 results, then it gives you back the values. So it's really useful, and it comes up a lot in JavaScript. Because the equivalent with callbacks is a bit hard to read. And it does not just work with arrays, it works with any iterable. So it's really good. You can put a map or anything and it will work. The only issue is that it will forget the original shape. Here you pass in a map of promises, but in the end, the VS value that you get back is an array. You've lost the map. So, Promise.all, it's great because it allows you to combine promises and collect results. So it turns a really nasty operation, if you do it with callbacks, into a really nice operation. It's a one-liner, it's cool. It works on any iterable, so it's good to not be tied with arrays. But the only issue is that in the process it forgets the original iterable. Okay, that was good. Now let's look at the equivalent in Haskell. I promise it will be fun. I will explain everything you need to know. Okay, so Here it is. Instead of calling Promise.all, I'm calling a function called sequence A. The trailing A is an unfortunate backward compatibility thing, but you can just read it as sequence and that would be nice. So sequence A, it takes a list of promises, so just like Promise.all, and the result, it's not like a promise. You don't have a then method, but you have something really close. In Haskell we call it bind, and it's written bracket bracket equal, and then you pass it a callback and you get your values. So it's really close to JavaScript. So it's essentially the same. The names are different, a couple parentheses are gone, but it's essentially the same. So this was a talk called It's Traverse, and now I'm telling you it's sequence. Yes, sequence and traverse are close, but in general we don't have like an array of promises lying around. In general we have an array of data, and then we have a query function that makes a request or stuff, and then we get our array of promises. So in general in JavaScript what we have is that we have like an array of user IDs. We map our getUser function that returns a promise of user, and then we call Promise.all on this. And it's so common that in Haskell there is a function that does the mapping and the collection in one go, and this function is called traverse. So here's the same thing. I've got an array of user IDs and a function that takes a user ID and return an IO of user. So here, these are not promises, but IO values or IO actions. In Haskell, every IO you do has to go through this. So IO is asynchronous by default, and it's really close to promises. The main difference is that in JavaScript promises are eager, and in Haskell IO actions are lazy. They are evaluated only if you need them, and they're not evaluated as soon as they are created. But it's the same. I call traverse on user IDs with my traversing function getUser, and then I get an array of users. Okay, so Promise.all was nice because it worked on any iterable. Is this the same with traverse in Haskell? Almost. It works on any traversable, which can feel a bit tautological, and it is, let's be honest. But it's just the same. The sign that traverse is really a core abstraction, because this function is important enough to describe its own class of types, so it means that it's quite important. Anyway, it works on lists, it works on maps, it works on trees, it works on really a lot of types. And it's even better than Promise.all because it does not forget shapes. Here I'm traversing not an array or list, but a map. So here I have a map from role to user ID, and then by calling getUser with traverse, I collect all the results in the map inside an IO. So here, small primer on Haskell syntax. The double colon mean that it's a type annotation, and all the type annotations are on separate lines. So here I'm saying that getUsers is a function that's noted with the arrow from map role user ID, so it means it's a map from role to user ID, to IO. IO is a bit like a promise of a map of where keys are roles and values are users. I call traverse the same way, and I get my original shape back. And even better than that, it composes. Here I don't take just a map of a role to user IDs, take a map of role to array to lists of user IDs. And I want to traverse both. I want to traverse the inner list and the outer map. And I can call traverse twice and it will work. And it will work this way for any iterable. It's not tied to lists or maps. It's just one traversable inside another one. And actually I can say that exactly to the compiler. Here I'm using a wrapper called compose, and it has no cost at runtime. It's just a marker saying to the compiler, I want to traverse both the map and the array at the same time. And that's it. And compose work for any two traversables. So it's even better than working on many types. You can combine types on the run, on the go, and it will do what you want. So going back to traversable. What is a traversable? You can really think of it as something you can call Promise.all on, but a bit more abstract. Here it's a simplified version of the type of traverse. A bit more syntax. The part before the fat arrow, it's called constraints on the types, and in Haskell all the types that start with a lowercase letter, it's a generic. So here the types T, A and B, they can be any type except for T. I had the constraint that it has a constraint on being traversable. So in English that would read as, for all T that is traversable, traverse as a type, it takes a function from A to I of B, and it returns a function from T of A to IO of T of B. So in essence what it does is that it gives you a B by performing an async effect, and then it collects all the created Bs and into a single IO value. And inside the IO you get your original collection. Okay, so many things are traversable, as I said, lists and maps and trees. But also maybe it's like optional in Java. So either you have a value or you have no value. And either as well, either it's called a sum type. It means that you can have either, let's say, a string or an int, and that's the type either string int. Yeah, that's it. We'll see a bit later about either. And it's really easy to make your own types traversable. Actually, in Haskell, you can have it done automatically by the compiler. Here I'm defining a binary tree type. So a binary tree, it's either a leaf, so terminal node, or a node with two subtrees, binary tree. And here I'm telling the compiler that I want it to implement automatically common behavior on this type. So I want to be able to check trees for equality. I want to display the value of a tree, yada yada yada. And in the end, what I need is for the tree to be traversable. Just with that, then I can call traverse on a tree and it will work as well. Nothing more to do. Okay, that's it for comparing traverse to Promise.all. Being able to generalize on any traversable type is super useful, because you get a map of promises, bam, you get a promise of a map. You don't have to recreate your map, you don't have to do any bookkeeping. Traverse does it for you. Not only that, but being able to compose on the go several traversable types and traverse them as well with no other bookkeeping to do is also really useful. Okay, that's nice. let's see if we can use it on something else. Another use case for Traverse is conditional execution. So I have, let's say I have optionally a new user. Maybe it's there, maybe it's not. And if it's there, I want to persist it to the database. Okay. So in regular code, that could be an if a user is defined, then persist user, else do nothing. But here we're on a talk called it's Traverse, so maybe it's Traverse. So here I've taken the signature of Traverse, but I've replaced the T, the abstract, the generic T, by maybe. So maybe represents a value that may not be there. And if I do that, okay, the first argument A to IO of B, that would be the save function. It would persist my user into a database, for instance. And then, given maybe a user, it would maybe perform IO and give me maybe the result of the insertion. Here, we're just performing a side effect. So in Java code, that would be a function returning void. And there is an analog of void in Haskell. It's called unit. It's the empty tuple, so the two parentheses. Here, I'm just saying that I don't care about the result. I just want something performed or not. And there is a function for that called traverse underscore. I give it a function performing an action, and it will perform the action if the value is there. Else, it won't do anything. So that's really useful. This one comes up really often, and it's really hard for people to notice it, even though it's super common. What I like about it, it's not always immediately obvious. So it's I think it's fun to have something not obvious like this. But what I like is that it showcases that in functional programming, you can use data structures for control flow, and that's super powerful. If you have a type system, it means that you can type check your control flow. It's different from in any imperative language. For instance, for loops and if blocks. There are control flows. They are not type checked by the compiler. In Haskell, since everything is an expression, all the control flow structures are typed. And more, you can create your own control flow because you can create your own data structures, and you can combine control flow operators as data structures. And that's really where FP shines, is that you can create your own control flow as like normal code and do what you want with it. You can unit test it, you can debug it, in some cases display it. You can do what you want, and you can play with control flow just like with regular data. Okay. Remember the signature of Traverse I've shown you earlier. I lied, it's not the actual signature. The actual signature is a bit more complex, but I think we're ready now to see it in its full glory. Okay, so here we don't have IO anymore. We are saying that traverse, it works for any T that you can traverse and any F that is an applicative. So it's the same signature. So instead of IO, that was capital letters, so that was a concrete type. No, it's a lowercase f. It means that it can be any f, and it's a generic, so it's up to the caller to decide which type is it. So, just maybe, you're wondering what the hell is a context. It's quite common in functional programming, especially when we deal with control flow with data structures, to not just talk about values like a user, but talk about values with context. For instance, it's a user that I got by performing IO. It's a user that may not be there, stuff like that. So it's a value, and we care about the value, but with additional information, and we still want to talk about the value itself and not and have something work automatically within the context without having to do the bookkeeping ourselves. And here it's not just a context, it's called an applicative context. What it means is that this context, we need it to be able to do a few things, to be able to use it with Traverse. And the most important thing we have to be able to do with our context is to be able to fuse two values in that context into a single context. So here I have two f's and I want to get a single one. And that's what applicative context allow you to do. Say, fuse effects in a way. They also provide two operations that we need. One is to be able to turn a regular value and put it inside a default context. And the other one is to map a function within a context. So if I have a function from A to B, I can apply it to a value of within a context, and it will just run the function inside the context without modifying it. Okay, I hope that was clear. No, I know it was not clear. It's super abstract and it takes time to really understand. So since we only get 1 hour, I will show you a few examples to get a feel of what's happening. But this is an abstraction that takes time to really understand. It took me months or years because I was not practicing FP full time at that time. Okay, let's talk about input validation. Have you tried to perform input validation with exceptions? Yeah, it's fun. Like, if it's not good, then you throw an exception, and that's nice. Have you tried to combine multiple validations with exceptions? And then not so fun because it crashes at the first exception and all the rest is ignored. In Haskell and in other languages, we have a tool for just for that. Let's say we want to perform a single check on several values. Let's say we have a list of numbers and we want to a list of string representing numbers, and we want to get actual numbers and get errors if the strings that do not represent numbers. In Haskell, we would do it this way. We have our parsing function. So instead of taking a string and returning an int, like it would be done in Java, for instance, we return an int, but within a specific context. And this context is that it can be an int, actually, or it can be a list of errors. Like, I was not able to parse the int, and here why I couldn't. So it can be, maybe it's an empty string, maybe the string contains characters that are not numerals, stuff like that. And that's the important part, how I parse a single string. If I want to parse an array of strings, then I can just slap traverse on it. I traverse my list of values with parse int, and then I will get, if everything goes well, I will get an array of ints, but if something goes wrong, I will get an array of errors. And here's a really nice thing with validation, is that it will accumulate all the errors. It won't stop at the first error. And that's really good. Especially the common case is a web form. Bad web forms, they show you one error at a time and you have to resubmit to get to the new error. And good web forms, they just give you all the errors they could find in a single pass. And that's exactly what validation is about. Being able to perform a check and return all the errors it found, not stop at the first one. So what we had a single check and multiple values. We can do it the other way. I have a single value, but I have multiple checks to perform on them. and it's the same, I want to aggregate all errors. Here, instead of having a single checking function, I have an array of functions. And since these are checks and not parsing, then I'm not really interested in the actual result. I just want to know if it was okay. If it was okay, then I can use the value. I don't need much more. But I just want to know if it's okay, then yeah, it was okay, cool. And if it's not, I just want to get a list of errors. And here I can also call traverse, but since we are not interested in the results because we just want to know it was okay, then we can use traverse underscore to discard the actual results and only keep the context. Here the context is that was it okay or were there some errors? And here I'm able to collect all the errors with a single function. And yeah, that's really great. Being able to easily combine errors, it's really good. Okay, let's try another context. At my company, we have microservices that we deployed on a platform as a service, and in this context, it's really the common way to configure them is through environment variables, and you can read environment variables like where you want in your code, but at some point, if you want to have proper error reporting and stuff like that, it's good to describe the expected environment variables in a single place so that you can get documentation. And as before, you want to your program to report all the missing variables in one step and not variable after variable. And here, saying, hey, I can parse this from the environment, yeah, it's a context as well. Here, I have my parsing function. So it takes as the argument the name of the environment variable, and it returns a parser. And I can traverse it, turn a list of string into a parser of list of string. Same. Good. Now we have seen several contexts. That's good, but did you know that contexts composed like traversables? Let's have a look. Here, I'm able to read a file. So I give a file path and I get an IO of string. So it performs IO and it reads the file contents and I get a string that is the file contents. Okay, that's good, but usually files are structured. Maybe I want to parse JSON files or stuff like that. So having a string is not enough. I need to pass this string into a more structured value. And here I can reuse validation that we saw earlier. I can turn a string into maybe a value if the file was syntactically correct, or a list of errors that happen when parsing the file. And those are two contexts. One context is I'm performing IO, and the other one is the parsing can fail. And I can compose them just like I composed Traversable earlier. So here I have a small helper function called read and parse. It takes a file path, it reads the file, and then within the IO context it tries to parse it. And then I use my old friend compose to tell the compiler, hey, I don't want to talk about these two contexts separately, I just want to fuse them into a single context. And I have my function, and I can use traverse with it. I traverse my list of paths with my parsing function. And then I get, within IO, maybe a list of parsed values, or maybe errors. And it will also accumulate all errors it got while parsing the files. It won't stop at the first file, it will try to parse every file, so I don't have to run it again and again to get all the errors. Okay. Now, remember when I said data is equal to control flow in functional programming? It means that for now we've seen on one side Traversable, so it's a bit like collections, it's a data structure, and contexts, which are more control flow structures, like validation and stuff. But since those two are the same, many applicative context types are also traversable. So you can have data structures on both the traversable and the applicative context. These are a few examples, but with those traverse, it lets me change representation and play with data structures in a really fast way. I don't have to write down all the transformation. Here I know that I can turn one type into the other. For this example, I will use sequence instead of traverse, because I think it makes things more easy to understand. So first function, I have a tuple, I have a value of type A, any type A, and an optional value of type B, any type B. And by calling sequence on that, then I get an optional tuple. So if B was defined, then I get my tuple, and if B was not defined, then I don't get anything. In a way, I'm losing information, because on the left A was always defined, and on the right A is not defined anymore. Another one, I have either a list of B or a single value A. I can turn that into a list of either an A or a B or a B. Here, if I have a list of B's, then the result will be a list of rights, and for each item in the left list I get a right on the right list. And if either was a left, so I only get an A value, then I get a list with a single element that is a left of A. But both either and list are traversable and applicative functors, so it works the other way. Coming from a list of eithers, I can get a single either containing a list. So what it will do there is that if all the eithers are defined and are B values on the left, then I will get my either of a list of B. It will move the either A outside the list. And if a single value in the list is an A and not a B, then I will get this value, and it will stop there. It won't collect values. I can do the same with validation. Validation and either are really close. They have the same runtime representation, but validation adds an extra constraint. It says that you can combine values of type A. And with this extra constraint, it means that when I collect all the B's into a list, I will also be able to collect all the A. So if I got multiple errors, it will be able to collect them. Most often, what we use as the error type of validation is a list of errors, or maybe a non-empty list of errors, because if we are in the error case, it means that there was at least one error. So we can have the compiler check that we never get an error with an empty list of errors. And the last example, it turns a list of function into a function taking a single function returning a list. What it does is that it takes one value and then applies it to every function and then collects the results. So here, you don't have to think a lot about what happens. You just look at the types and it does what you expect. Especially when you work with abstract types, there is only one sensible way to do things. So just looking at the type is enough. And actually, just looking at the type is a good thing to do, because if you are chaining multiple traverses on multiple data types, the implementation will be just traverse sequence, and it's not super readable. But you don't need to be able to read that, because the types will tell you anything you want. So, what did we learn today? The abstractions coming from math mostly, and they take some time to and some work to learn, but they are really precise and they exist outside programs. They have their own existence. So we're not tying our model to something to technique or to programming languages. What is a monoid does not depend on your version of Spring Framework. You won't break monoids by upgrading Hibernate or stuff like that, and that's really powerful because it's an investment that will not rot. It's a good investment because it won't change. And Traverse, it's extremely versatile because it's polymorphic on two axes. It works on any traversable and it works for any applicative functor. And this double axis of genericity, it means that there are lots and lots of combinations possible, and each combination gives rise to a new use case that can be different from the other use case. And especially since you can compose both traversables and context on the go, then you can you have a combinatorial explosion of possibilities again and again. So it can happen everywhere because it's so generic. And especially in FP, this duality with between control flow and data structures means that all these data transformation, they can map to control flow manipulation functions, which is super powerful. Okay, I hope that I've shown you that good abstractions, they change the way you think, because now when I think about code, I think about abstractions. I think about functors, I think about monads, traversables. I don't think about implementation. And when I'm looking at code, most of the time I look at the types and the abstractions. And from time to time I really need to look at the actual implementation. But most of the time, looking at the types is enough to give me a good feeling of what happens. Of course, I have tests and everything. Don't worry, I'm not like a madman. But I'm able to skip a lot of uninteresting details to get a feel of what code does. And especially, these abstractions, they usually come with laws that are immediately usable as unit tests or property-based tests. So there are libraries that gives you both the abstraction and the collection of tests it has to pass. So if you want to implement an abstraction, implement behavior for a given abstraction, then you also have the checks provided to make sure you're not doing unlawful, as we say, implementations. And that's the first thing. If you know these abstractions well, you will think a bit differently, and that's already great. But if you're working in a team, well, everybody shares a common ground of abstraction, then it changes the way you communicate with your colleagues. And it's the same. You're able to talk about high-level concepts and don't get lost into details, because abstractions, they enable you to separate uninteresting details from what you actually want to talk about. And that's super powerful. Of course, that means that your team has to learn and to come up with a list of abstractions you agree upon and that everybody knows. But that's definitely a good investment. And yeah, to finish, I want to go back to, hey, it's a for loop joke I told earlier. It's not really a joke, actually. There is a paper called The Essence of the Iterator Pattern that shows that Traverse captures and expands upon the for loop. So that's why Traverse is so pervasive. It's as fundamental as a for loop. And it's even more fundamental as a for loop because it also works on data structure and control flow. And yeah, that's a great paper. You can read parts of it. There are some proofs that may not interest anyone, or maybe implementers, but they are really nice things. What I liked most is that it showcases how you can compose context in different ways. I've shown one way to compose context it was nesting them, but you can have context side by side, and it shows that with a word count example where you traverse text and you aggregate different counts on the same path. So you describe your counting methods and then you compose them, and boom, you traverse with the composition. It's great. Okay, thanks. I know this was quite abstract and a bit more abstract than usual DDD, but I assure you it's really nice to be able to talk about a domain with common properties that you can reuse across projects. Thanks.
Thank you, Clément, for your interesting talk. We need to start moving on, and if you want to continue the conversation, please use either Twitter, the hashtag with 5xD, or you can go to the virtual DDD Slack channel on the DDD CQRS Slack. There's a link on the virtual DDD page. Thanks for now. Thanks, Clément, again, and we hope to see you in another session.